Okay, now let us start our class today. We're going to continue with a 6.3. There's still a bit of a 6.3 that we haven't done discussing yet last week. And then we will finish off with chapter 6 today, 6.4 as well, okay? So now let's look at the resonance in AC circuit. In a previous lesson, in our class last week, we have seen what is a pure R, okay, pure R, and then a pure C, pure L, and then RC, RL, and RCL circuit. We have gone through all these 6 types of circuit last week, and then we learned how to sketch its phasor diagram. So if you remember, okay, when it comes to pure resistor, okay, the phasor diagram, both of them, they are heading toward the same direction, meaning that both the current and the V, they are in phase. Okay, your VR and I, they are in phase. When it comes to C, okay, when it comes to C, now I, it's leading. So provided if you put the I along the X component, then it means your V would be going downwards. Okay, if you put the V on the X component, then the I will be going upwards. Depends on the equations given. When it comes to L, okay, now let's say your I is still lying on the X component. Now, when it comes to inductor, we know that in an inductor, oops, just now should be VC. So we know that in an inductor, okay, the voltage, the V, it should lead I. Therefore, if your I is lying on the X component, then we have VL pointing upwards. Then how about the combination circuit? Okay, these 3 combination circuit. Now, when it comes to combination circuit, actually it's very simple. You just stack the phasor diagram from the pure circuit. Okay, you stack them on top of each other, then you are going to get a new phasor diagram. For example, RC. RC, we know that pure R is, okay, the VR and the I, they are in phase. So VR and I, I'm just going to write it down. And then when it comes to VC, okay, if your I is lying on the X component, VC should be heading downwards. Therefore, for RC circuit, your VC is going down. That is what we learned last week, all right? And then RL, then how about RL? Once again, I'm going to sketch the phasor diagram for VR and I first. Okay, so provided I'm assuming my I is lying on the X component, it starts from 0. Then VR is in phase with I. When it comes to L, L leads I. Therefore, my L is going upwards. So that is the phasor diagram for RL circuit. And when it comes to RCL, you just stack these 3 diagrams, these 3 phasor diagrams on top of each other. So VR again, okay, they are both pointing to the right-hand side. Oops. VC is going up. And then not VC going up, VL going up, and then VC going down. So that is the phasor diagram. The things that you have to be careful is just the magnitude for VC and VL. Why? Because now you are looking at phasor diagram. Phasor diagram, phasor is a vector. So when it comes to a vector, what does it mean? The length of the vector, it represents the magnitude. So if your VL is larger than VC, then the length for VL should be longer than VC. Okay, the length of the arrow. But if your VC, the magnitude of VC is larger, then the length of the arrow for VC, it should be longer than VL. So keep that in your mind. When you're looking at vector, when you're looking at phasor, then you have to take into consideration the length of the arrow, because length represents magnitude and the arrow represents direction. All right? So that is a quick summary for phasor diagram. Once you have phasor diagram, then pretty much you can do almost everything in chapter 6. Why? Because from phasor diagram, you know how to calculate the V source. Okay, you know how to calculate V source by looking at the resultant. And then you know how to calculate the impedance, the Z. And you also know how to calculate the phase angle. So from phase angle, it will tell you the relationship between I and V. Okay, which one is leading, which one lags behind. Okay, whether the source voltage is leading or lags behind the current in the circuit. Okay, so basically that is a summary up until 6.3. Now we're going to continue with a resonance. So other than 6 types of circuit, we have also learned for another 2 Okay, we have also learned another two equations, which is the XC and XL, that can be used to calculate impedance, right? So in order to calculate impedance, okay, we are going to need R and then XC and also XL. So now today, in a resonance, we are going to focus on these four variables, which is Z, R, XC, and XL. Now, by looking at this R, okay, what is a R? Okay, R is just a resistance. And a resistance, it does not depend on the frequency. That's why it doesn't matter whether you change the frequency of your source voltage or not. Okay, your graph, your values for V and I, they are always constant. They won't change because your R, it does not depend on frequency. So by changing frequency, it won't affect R, and thus it won't affect the current flow in the circuit. Therefore, when it comes to R, okay, wait there, let me find a place to write it down. So we have Z, and then the first thing we're going to look at is R, XC, and XL. So when it comes to R, okay, when you're plotting a graph of R against frequency, since R, it does not depend on the frequency. So if you're just going to plot a graph, okay, a R against F graph, then you are just going to obtain a straight line. Meaning that R is always a constant value, regardless of what is the frequency of the source voltage. Okay, that's why when you plot a graph, okay, when you plot a graph in a diagram, okay, in a F against R diagram, the first thing that you have is the R is a straight line. Okay, you look at the diagrams at the center in your notes. So you have R, okay, you have R lying, you have R lying on a horizontal line that is parallel to the X component, X axis. Now, how about XC and XL? Try to ask yourself, what is the equations for XC and XL? So if you look at XC, the equation is 1 over 2 pi FC, in which if you are using the same capacitor, remember, if you're using same capacitor, then C is constant. Meaning that if you look at this equation, okay, if you look at this equation, it tells you that XC, it depends on the frequency. Why? Because it is inversely proportional to frequency. Okay, if you are still using the same capacitor, so when you change the values of frequency, XC changes. Therefore, when you plot a graph for XC against F, what is going to happen? Since it's inversely proportional, therefore you got a graph, okay, like this, okay, a curved graph like this. Now remember, it won't touch the Y component, okay, it won't touch the X component as well. All right, so XC against F graph, that is the shape of the graph. Why it won't touch a 0, it won't touch a Y-axis and X-axis? Because you cannot divide 0, okay? You cannot use 1 divided by 0. If you say it touch a X-axis, then you're assuming your X is 0, XC is 0. If X is 0, then F would be 1 over 0. Then it would be an invalid equations, okay? So when you sketch a graph, okay, when you sketch a resonance graph, remember when it comes to XC and F, it won't touch both Y component and X component. Okay, it will goes up to infinity because you cannot divide by 0. If XC divide by 0, then what is going to happen? It's going to be equals to infinity. So remember, it won't touch. Now then, how about XL? If you look at the equations for XL equals to 2 pi FL, in which it tells you now your XL is directly proportional to frequency, provided your inductance is a constant value. If you're using the same inductor, but now you change the values of the frequency. Okay, now what are you going to get? You're going to get a linear graph because it is directly proportional. So when it comes to XL against F graph, you're going to get a straight line graph. Okay, you're going to get a straight line graph. So when you combine these three graphs together, what are you going to get? You're going to get a graph for Z. And that is the shape of the graph. Okay, if you look at the diagram, that is the shape of the graph that you're going to get. If you combine these three graphs together, okay, when you calculate the resultant of all three resistance and reactance. All right. Now, if you observe this graph, if you look at this graph, what happens when your XL is equals to XC at this point? So when your XL is equals to XC, we know that Z is equals to R. Okay, why? Because XC and XL, they cancel off each other, as shown in a bullet point D. So from figure, the values of impedance is minimum, okay, is minimum when XL equals to XC. Why? Because when XL equals to XC, okay, they will give you 0 in the calculation. Therefore, Z minimum at the same time, it is equals to R. The minimum impedance that one circuit can have, it is when its value is equals to R. Okay, so Z min, it's equals to R at its maximum value, okay, at its minimum value when XC equals to XL. Okay, when XC equals to XL. So that is the condition. Sometimes questions won't tell you whether the circuit is resonant or not, but you yourself should know when XC equals to XL, okay, when XC equals to XL, then it means we are having the resonant frequency. Okay, that's why if you look at the graph, it tells you at this point, this F, we call it FR. So that is the resonant frequency, which it happens at XL equals to XC, and it happens at when your Z is equals to the values of resistance. All right? So that is the resonant frequency, the condition. So FR, it happens at two situations, when your XC equals to XL, or when you have a Z minimum, which its value is equals to R. Right? So sometimes questions, it won't tell you, okay? Remember, questions won't tell you that you are having a resonant frequency right now, but what it tells you might be now you have XL equals to XC. Then you yourself have to know the frequency is a resonant frequency. Okay, it's referring to the resonant frequency. So at resonant frequency, okay, at resonance in the RCL series circuit, the impedance is minimum, and thus RMS flow in the circuit is maximum. Okay, why? Because by looking at this equation, we have I is inversely proportional to Z. Okay, I is inversely proportional to Z. Therefore, if you are having minimum Z, then you will have a maximum current in the circuit. Okay, the current is maximum. So the resonant frequency, how are we going to calculate resonant frequency? Since the equations come with frequency is XC and XL, then we are going to start to derive it from this relationship. When XL equals to XC, omega L, or we say 2 pi FL, is equals to 1 over omega C. Rearrange the equations, we have omega squared equals to 1 over LC. Omega is equals to 2 pi F, but now this frequency, we call it resonant frequency. So when you rearrange the equation, resonant frequency, it's actually equals to 1 over 2 pi square root LC. So this is the equations that can be used to calculate resonance frequency. Okay, this is the equations that can be used to calculate resonance frequency. So right now, I give you some time to write out a bit of a summary and also how to obtain this graph. Okay, now previously when it comes out in the exam, okay, it likes to ask students to sketch this graph. So make sure you know the shape. Okay, you know how to sketch the graph, and you also know the relationship between XL and F as well as the XC and F. Okay, that is the things that you have to know. And the reasons why my R is a horizontal line, that is because it does not depend on the frequency. Okay, R does not depend on the frequency. That is the things that you need to know. Okay, it does not depends on F. All right, so I give you a few minutes to write it down before we proceed to the new subtopic. Okay, so that marks the end of 6.3. We are done with a phasor diagram, and then we are done with the resonant frequency as well. Okay, so 6 types of circuit together with resonant frequency. That is everything's in 6.3. So I give you a bit of time to write it down. Okay, so now let's look at the power. Okay, power in pure R, pure C, and pure L circuit. So how are we going to sketch the power for the graph for the power? First things you have to know that your I and V, it keeps changing. Okay, it changes with time. Meaning that for power, we have to derive its equations as well. We can't get a straight line graph. Okay, because of what? Because your I and V, okay, both I and V, they changes with time. So when it comes to this case, then we need to know how to derive a new equations that can be used to calculate power at different time, at a particular moment. So in order to sketch the equations, okay, we're going to apply the equations power equals to IV. Okay, since you want to sketch a graph for power, then we're going to use instantaneous P. Okay, because we don't know. Okay, we don't know what is the power that we want to calculate yet. So what are we going to do? We use instantaneous P, okay, equals to I instantaneous and V instantaneous. We need to derive an equation for P in order to sketch the graph for it. So how are we going to sketch? Now let's go back to the table. Okay, the reasons why we use these equations, that is because V and I, it changes with time. So in this case, we are going to derive an equation. So in a pure resistor, the voltage and current, they are in phase. Thus, the instantaneous power, okay, instantaneous power is given by P instantaneous equals to I instantaneous, V instantaneous. Okay, so I instantaneous and V instantaneous, when it comes to R, remember, okay, for R, I and V, they are in phase. So I equals to I naught sine omega t, V equals to V naught sine omega t. Okay, they are in phase. So when you apply these two equations, when you sub these two equations into equations for P, then you obtain I naught V naught equals I naught V naught sine square omega t equals to instantaneous power. Okay, so your P instantaneous in this small box, you write it as now P naught, I naught and V naught, it will then give you P naught, which is the peak power. Okay, peak power sine square omega t. Okay, sine square omega t. Now, peak power, it doesn't represent, well, I wouldn't say it doesn't represent. It depends on the graph. Okay, where is your peak power? Okay, the peak power in your calculation, it does not represent the maximum value in the graph. Okay, we'll look at it in a bit. Okay, we'll look at it in a bit. So don't get confused between the peak power and the maximum power. Okay, so for pure resistor, yes, peak power is equals to maximum power. Okay, that is based on the graph. So if you look at the graph given, okay, you look at the graph given. Okay, we are going to look at them column by column, ya. So kita tak tengok C, tak tengok L lagi, kita tengok pure R dari atas sampai ke bawah dulu. Sebelum kita tengok seterusnya. So pure R, now you obtain an equations P equals to P naught sine square omega t. From here, you then plot a graph. Okay, and this is the graph that you obtain based on the equations that you derive. So figure shows a graph of instantaneous power being absorbed by the resistor against time. Okay, against time. So by looking at these equations, now we obtain a graph P against T. So this is the shape of the graph, okay? Because we have a sine square, so the graph is much larger compared to the normal graph that we have. And because it is a square, okay? So when it comes to a square value, means that you don't have negative part, okay? Negative y component. So now this whole thing is lying on the positive component. So all of the energy, they are being absorbed. And then what happened after they're being absorbed? They are being used by the circuit. Absorb and use. Okay, so your power, all this power, they are being used to do works in the circuit. So the maximum value, according to this graph, is the P peak. Okay, if the peak value, peak power. So that is the maximum value for this particular graph. So P against T, that is the graph. And what is the average power? Average power means it's the mean power. Okay, the middle line. You just draw a line at the center. So the average power being absorbed by the resistor is given by, okay, P average is equals to, now you're going to calculate the average value. So according to the graph given, okay, the mean, the average is P naught over 2. Okay, di tengah-tengah. Between maximum and minimum, the center between max and min is P naught over 2. So therefore, average power is half of the peak value in your pure R circuit. So by substituting P naught equals to I naught V naught, okay, and then I naught is a square root IRMS, and then V naught is a square root VRMS. Now, something is missing right here. Okay, sepatutnya ada satu half di sini. Okay, you should have a half right here. So this half, okay, this half times square root IRMS square root VRMS. Therefore, average power at the same time, it is equals to IRMS VRRMS. All right, because now you are looking at a pure resistor. So this V, okay, this V by right, it should be VRRMS. Therefore, when it comes to calculating average power in a pure R circuit, your P average is equals to IRMS VRRMS. Okay, VRRMS. So this is very, very important. Okay, this is very, very important. We will find out why very soon. Right now, what I want you to do, okay, you make a bit of correction in your books, in your textbook. Okay, half is missing right here. Okay, yang 1/2 adalah hilang. Buku kamu dah tercicir. So 1/2 square root 2 IRMS times square root 2 VRRMS. So R ni, okay, you make a note there. This is the VRMS across resistor. Okay, VRMS across resistor. Be extra careful with all this value, because usually you will have 3 to 4 types of V in one question. So you yourself have to know which V to be used in your calculation. All right. So P average is equals to IRMS VRRMS. So for resistor, okay, you derive, you obtain P average is equals to IRMS VRRMS. Now it's very important now for average value. Why? Because peak value, well, we seldom use peak value in our calculations, because your circuit, it won't always remain maintained at its peak value, peak power. Okay, so as you can see right here, it keeps changing from 0 to maximum, go back to 0 to maximum again. So a more useful value that can be used to show the real power that's being used by the circuit is the average value, okay, rather than the peak value. Now let's look at pure, okay, let's look at the pure L and pure C circuit. So pure C circuit, okay, if you look at pure C circuit, in a pure capacitor, the current leads voltage by pi over 2 radian. Okay, so what happens right here? We have the equation. Now, since you are using the, okay, if you look at the equation, since you use cos for I, then you use sine for V. Okay, because their difference, the phase difference between I and V is pi over 2 radian. If the phase difference is pi over 2 radian, then it means one will be using cos and the other one will be sine. So I naught cos omega t times V naught sine omega t. What happens? Okay, when you calculate it, you obtain I naught V naught sine omega t cos omega t. Now, according to a trigonometry functions rules, sine omega t cos omega t at the same time, okay, your sine theta cos theta at the same time is equals to 1/2 sine 2 theta. Okay, half 2 sine theta, half sine 2 theta, sorry, half sine 2 theta. Okay, so that is according to your trigo identity. Then from here, we can then simplify the equations and obtain, okay, P instantaneous is equal to 1/2 P naught, okay, 1/2 P naught, because you're going to keep the I naught V naught here, so it becomes P naught. So sine omega t cos omega t is sine 2 omega t. Okay, sine 2 omega t. So that is the instantaneous in a pure C circuit. Now, when it comes to pure L, because the phase difference between V and I is once again pi over 2 radian. So when you derive the equation, the instantaneous power in pure L circuit is exactly same as the instantaneous power in pure C circuit, which is 1/2 P naught sine 2 omega t. We obtain this one because of what? Because of the trigo identity, sine theta cos theta equals to 1 over 2 sine squared, sine 2 theta, sorry. Okay, sine 2 theta. So when you plot a graph, okay, when you plot a graph according to this equation, based on the equations given, so this is the type of the graph that you're going to get. So figure shows the graph of instantaneous power of a pure capacitor and pure inductor against time. So now you have a sine 2 omega t. Okay, it is not sine square. Therefore, you're going to have a positive and a negative y component. Now, by looking at this graph, okay, so the maximum value in your graph, okay, the maximum value in the graph, it's 1 over 2 p naught, okay, because that is the values that you have in front of your trigo functions in equation. So 1 over 2 p naught, it represents the maximum value that you can have. So P naught, okay, the peak value divided by 2 is the maximum powers that you can have in a pure C or a pure L circuit. All right, that's why, like what I told you just now, peak power, it doesn't represent maximum power. It is only true in pure R circuit, but it is not true for pure C and pure L. Okay, in pure C and pure L, P peak, it doesn't represent P maximum. P maximum, according to the diagrams given, it's equals to half peak value, half of the peak value. Now, again, if you look at this graph, now because you have a positive power and negative power, then what does it mean? It tells you when your power is positive, the power is being absorbed by the component, by the capacitor and inductor. And when it goes back to negative, then it means the power is being returned to the supply, it's being released. Okay, so what happens right here is it tells you, okay, your capacitor and inductor is just going to receive the power, okay, receive the power in the first half cycle, and then after that, it gives it back to the supply, okay, it gives it back to the power supply. So what happens right here? Receive, return, receive, and then return. Unlike your resistor, it receive and then it use up, receive and then it use to do works. When it comes to pure capacitor and pure inductor, what is happening is just take the energy, it's stored. Okay, it store the energy in the capacitor and also in the inductor, and then after that, it give it back to the supply when you need it. Okay, it release it back. So, okay, if you look at this diagram, okay, which it means if you are going to calculate the average value, remember what does it mean by average value? Average value is the midway of your maximum and your minimum value. Maximum value right here, you have P naught over 2. Minimum value, you have negative P naught over 2. So the midway is equals to the midpoint between P naught over 2 and negative P naught over 2 is 0. So the average power of the pure capacitor and the pure inductor is given by P average is equals to 0. Aha! So your C and your L, they tells you P average is equals to 0. No power is being used, okay, in your capacitor and inductor. Which it means if the question asks you to calculate average power in a circuit, it doesn't matter whether it is RC, RL, or RCL circuit. What you have to know is that the only power that is being used, the real power that is being used to do works, is just the power that's coming from your resistor. Okay, that's coming from your resistor. That's why when questions ask you to calculate the average power, it doesn't matter what type of circuit that you are looking at, the average power PAV is always equals to IRMS VRRMS, regardless of how many components you have in the circuit. Dia tak kisah. Sebab apa? Because of the average power passes through, okay, across your capacitor and inductor is always equals to 0. So when you calculate average power or when you calculate the so-called real power, then you just calculate the power across resistor. Okay, kita cuma kira power across resistor. So we obtain this conclusion based on the derivation, based on the graph. Okay, so these two graphs is very important. It tells us how to calculate average power, and it tells us what is peak power, what is maximum power. Okay, what is the relationship between peak power and maximum power. All right. So, well, I give you a few minutes again to write down some of the notes. Okay, buat sikit catatan. yang Anda rasa mungkin Anda perlu buat catatan dalam buku Anda. Okay, okay, start again. Wait, let me restart it. It's stuck, it won't move. All right, so I give you a bit of time to write down some of the additional info, okay, additional info from here, and also the correction. Don't forget about the correction, all right? Okay. So write down, then we will proceed to the next part. Okay, we're going to see what does it mean by average power and what does it mean by apparent power and how to calculate the power factor. All right. So now let's look at the next part. Okay, next part, it tells us why, reasons why we want to calculate average power instead of instantaneous power. Okay, so the instantaneous power absorbed, okay, wait, yeah. Okay, absorbed by or transferred to a circuit element, which is the components in the circuit, is the products of a potential difference instantaneous across the I instantaneous flowing through it. So mathematically, okay, like what we derived just now, how we did it just now, P instantaneous is equals to I instantaneous, V instantaneous. Okay, they are coming from the same family. So in many cases, we are not interested so much in the instantaneous power, okay, over a complete cycle of its oscillation because it's keep changing. Okay, it won't give us much information. All right, if it keeps changing, then what is the values that we're going to use, right? So that is not the things that we want. What we want is the effective value. So how to obtain effective value? Of course, we are going to calculate from effective value, right? So effective value can be calculated by effective value. So a real power is the ones that we want. Okay, so real power, it performs a real work, okay, within the electric circuit. Real power is defined by the power consumed, okay, power consumed by the resistive part of the circuit. So if you have a circuit that contains R, C, and L, the one that consumes power is just the resistor, okay, it's just a resistor. So it will consume power. The other two, it just react. Okay, it just react. How does it react? React by receiving and returning. Okay, receiving and returning the power to the circuit. It doesn't consume any power. So then the real power in an AC circuit is same as the power in the DC circuit. Okay, that's why we calculate real power, because it is the power consumed by the resistive part. And we are going to say it is same as the power that we use in a DC circuit. because yes, we are looking at the consume, the effective power that is being used by the circuit. So as resistance do not produce any phase difference between voltage and the current waveform, all the useful power is delivered directly to the resistor and converted to heat, light, and works. Okay, they are all being used up. Then the power consumed by resistance is the real power, which is fundamentally the circuit average power. Why? Okay, the reason why we say it's average power, because when it comes to C and L, average power is equal to 0. What is happening? It's just receive and return. None of the power is being used. But the average power in the R, in the resistor, okay, is half of the peak value. So in this case, okay, what are we going to say? P average is equals to PR. Okay, so PR, it stands for P real. Okay, so PR. So PR at the same time, it is equals to what? Now, since we are looking at effective power, then we're going to calculate it by using effective value, which is IRMS VRRMS. Okay, VRRMS. The reasons why we use VRRMS, because R is the only component that consume power. Okay, consume power. So it is also equals to IRMS and then V source cos phi. Now, provided if you have an RCL circuit, okay, then this would be the phasor diagram. So this is your VR, this is your I, this is your VL, this is your VC. Okay, then source, let's say source is somewhere here, VS. So the relationship between the source and the VR, okay, is a cos phi. So this is your phi. Okay, this is a phi. So cos phi is equals to VR over VS. Okay, VR over VS based on the diagrams given. Therefore, VR at the same time can be written as VS cos phi. Okay, VS cos phi. So that is what we have in average power. Okay, I give you 2 minutes to write down the diagram so that you understand how to obtain this VS cos phi. Okay, datang dari mana VS cos phi ini. So you sketch the diagram and then you show the derivations on the right hand side. Okay, so that you can see where does it come from. And also write down the equations. Make sure write it down with all of the subscript. Okay, especially the subscript R across your RMSV. Okay, your RMSV. So 2 minutes for you to write it down, the diagram, the derivation, before we proceed to the last part, the last page of chapter 6. All right, now let's look at the last page. Okay, let's look at the last page. Okay, so just now we're looking at the real power. Okay, there is another type of power in our AC circuit, which we call apparent power. So the current and the voltage waveform are not in phase due to the phase difference between circuit resistive and reactive component. Now, you see, just now we were looking at resistive component when it comes to real power. In apparent power, we are looking at both resistive and reactive component. So the product of RMS voltage applied to the circuit, which is your V source, okay, and the RMS current flowing through that circuit is called apparent power. So now we look at source voltage. Okay, how many voltage, okay, coming out from the source? So from there, we then calculate apparent power by using PA equals to IVS. So apparent power is the total power consumed by a circuit, even though the real power does the work a lot less. Okay, so basically what I would say this is more like the power supply, okay, the power supply, because it's coming out from a source voltage. So not all power supply, they are being consumed by the circuit. Some of them, they are just being received, okay, absorbed, and then it will returns back to the supply after a while. So this PA is equals to IVS, so apparent power. So apparent power, this V is the source voltage, okay, it's a source voltage. Now, and of course, when it comes to calculations, to be more precise, this PA is actually equals to IRMS VS RMS. Okay, VS RMS. So you're looking at the RMS value, all right? You're looking at the RMS value. So apparent power is the total power consumed by both resistive and reactive component. Okay, resistive and reactive component. So power factor, okay, power factor is defined as the ratio of real power to the apparent power. So you want to look at the ratio of the power that do works and the total power supply. So this is the ratio, okay, a ratio. Now, what does it mean by ratio? Ratio means that this value, this power vector is dimensionless. Okay, dimensionless. What does it mean by dimensionless? Mean that it has no unit. Okay, no unit. It is a value without unit. So power factor, remember, it is a value without unit. So mathematically, because you are looking at the ratio of P reals over P apparent, so cos phi, it's equals to PR over PA. Okay, over PA. So that is the equations that we use to calculate power factor. So power factor, this cos phi, the whole thing, it represents power factor. Okay, not the angle, not tangent phi, not sine phi, but the cos phi. Okay, because cos phi will give us the ratio of PR over PA. Okay, over PR over PA. Okay, now, when it comes to this part, actually there are a lot more of equations that can be used to calculate power factor if you derive the equation step by step. So cos phi, we know it is PR over PA. PR, we know that it is equals to IVR. Okay, they are all RMS here, but I'm just going to write it as I and V, because if I write RMS, the whole thing will become very messy in the derivation. All right, but all the things I'm writing here, they are all RMS value. So PR is IVR. PA is IVS. Okay, PA is IVS. So you can also use the equation VR over VS to calculate your cos phi. Okay, to calculate your cos phi. And then, there's another one equations that can be used to calculate the value, which is, now if you look at this step, okay, if you look at this two diagram, the R here, okay, the R right here, VR and VS. Now, since we know VR at the same time is equals to IR, and then VS at the same time is equals to IZ, okay, IZ. So these equations can then be written as IR over IZ, okay, IR over IZ. So from here, what are we going to do? Okay, we're going to simplify the equations again. Okay, we're going to simplify the equations again. And cos phi at the same time is equals to the ratio of r to z. Okay, the ratio of r to z if you do the derivation. Okay, so when you look at this set of equations, you can then sum it up as, okay, cos phi is equals to PR over PA. It is equals to VR over VS. It is equals to R over Z. All these equations can be used to calculate power factor. Okay, can be used to calculate power factor. So basically, basically you can calculate power factor by looking at the phasor diagram as well. So power factor is the phase difference between current and voltage waveform, where I and V, they are the magnitudes of RMS value of the current and voltage. Remember, I and V, they are always the RMS value. Okay, so you can always calculate power factor by looking at the phasor diagram as well. That's why I keep telling you guys, phasor diagram is the most important things in chapter 6. From phasor diagram, you will know how to calculate source voltage. From phasor diagram as well, you will learn how to calculate impedance. You know how to get the values of phase angle. And right now, there's one more thing that can be calculated by using phasor diagram, which is the power factor. So from this diagram, just now we were doing it according to the derivation. But now if you look at this diagram, you have angle here. Okay, this is the angle. So in order to calculate cos phi, by looking at phasor diagram, straight away I know cos phi is VR over VS. If you're looking at the phasor diagram for impedance, so this would be your R, this would be your XL, okay, and then this would be your XC, and this is your Z, and this is a phase angle. By looking at this phasor diagram, once again, straight away you can obtain cos phi is equals to R over Z. Okay, R over Z. So basically, you don't even have to memorize the equation. All you have to know is the phasor diagram. If you know the phasor diagram, then it shouldn't be an issue for you to determine power factor, phase angle, V source, and also Z. Everything is coming from the phasor diagram. All right. So now you just sketch the diagram, okay? You just sketch these two diagrams and also the derivations on the right-hand side into your book. Okay, buat sedikit catatan. Supaya Anda tahu, bukan sahaja boleh kira daripada equations di sini, okay, this set of equation, straight away you can get it from the phasor diagram as well. Sekiranya dalam exam, Anda terlupa macam mana dapat pengiraan, then you may refer to the phasor diagram. Why? Because the list of formula given, they will just give you this equation if I'm not mistaken. Okay, PR over PA. So you yourself have to know how to calculate and how to use all the other equations. So all the other equations, either you get it from the phasor diagram, okay, or you got it from the derivations on the right-hand side. So write it down, okay? There are plenty of a blank space in your books because this is the last section. So I think there are half empty page in your book. Write it down, sketch the diagram. It would help a lot if you know how to use phasor diagram.